Okay.
We're ready.
Yes, we're ready.
We're here celebrating the 11th Annual Encephalitis Conference here in North America, FACES 2014 Encephalitis Conference. My name is Wendy. I'm president of Encephalitis Global, and I am an encephalitis survivor.
And I'm Dale, and I'm on the board of directors of Encephalitis Global, and I'm an encephalitis survivor.
And I'm Ingrid, and I'm an encephalitis survivor since 1995, and I am also on the board. And in addition to celebrating our 11th meeting, we are also celebrating the International Encephalitis Day, the first one in
the World
Encephalitis Day with the British Encephalitis Group. So we're here, and this is our largest crowd this time, and we're having a great time. So.
Excellent large crowd.
Yeah, really great. So.
Well, thank you very much for coming to town. This is a very exciting group, and thank you for inviting me to talk. I'm going to talk about our program here at the Brain Observatory, which is a brain library. It's an archive of imaging data, MRI, and brains as well. And in fact, I brought the brain, not the real brain, of one of our patients. Now with 3D printers, we can actually reprint the brains that we image. So, and this is actually a patient who had a lesion in the medial temporal lobe, so you can actually see the gap. It's very interesting to reprint our brains because there's something about the way that we examine with our tactile sense as well an object that you can never replicate in a monitor. So I'm very happy about this new technology. And it's a box that it's on our desk, so wonderful, yes.
I won't let you take mine out.
I have the tool right here. If you I always carry it with me. So, Brains in the Cloud. The idea of this project is to create an archive on the web so that doctors, advocates, and policymakers and students and educators, they can gather information from, imagine like a Wikipedia or a Library of Congress that describes the human brain. And our initial assumption, let's say our axiom for this project is that every brain is different, every person is different, and even the way that the same disease operates in different people is different. And so instead of creating an average map that represents the human brain, our effort, we're trying to catalog, we're trying to describe as many human beings as possible from a neurological point of view. So imagine creating neurological portraits. Remember the song, you know, if I were a painter, if I were a sculptor, but then again, no, well, I'm not a sculptor, I'm not a painter, I'm a neurologist. So the portraits of my patients look like this, my sculptures, and my paintings are images from MRI and the microscopes. Now, this person is maybe one of the most well-known or famous, at least in the medical circles, patients that we had the honor to work with. His name was Henry Mollison, and he taught us a lot about the brain. So now I'm going to give a little bit of introduction about the imaging, what we do these days, what tools we have at our disposal. And these images here are images of 3 different individuals who participate in our program, and they have different ages. So you see there's something that happens to the brain. There is a process of aging, just like our body, our brain ages as well. And there are effects that are very clear. You know, for example, I don't have a laser pointer because I used all the battery playing with my cat. I'm sorry. So this morning I realized, no. So I will have to point. So you see, these are the ventricles. These are cavities that are filled with cerebrospinal fluid inside the brain. And one thing that happens during aging that we see with MRI is that they get bigger. They get bigger because the mass of the brain decreases and the body compensates by pumping more fluid inside the brain. Now, you can see a 93-year-old, the brain doesn't look as turgid and as healthy in many respects as that of a 50-year-old, which I'm approaching. So let's hope that my brain looks at least like that, despite the red wine. But you know, this is so you would think this is bad news because, oh my God, now look at my brain, it's shriveling inside my head just by aging, and it's nothing we can do. But the good news is that the brain that you saw on the right actually belongs to Beth, who is a very healthy and mentally healthy and very feisty and an intelligent 95-year-old now woman. So, the fact that our brain doesn't look as good when we get older doesn't mean that we cannot function well. And we realize gradually that also the attitude towards aging influences and personality influence the way that we use our brain. And this is a new field of study in general. This is Beth again in her more, I would say she looks very innocuous here, but she's not. Beware. But now what we study in our lab is also memory. And this is one of the central points, I think, in our cognition, because memory defines who we are. At least the way we perceive ourselves is based on the memories. There are some spiritual methodologies, and including yoga, if we consider that spiritual practice, that tend to train the person to live more in the present. And that's actually very difficult to do, because we're certainly always haunted by our past, and we're always trying to make predictions on the future. It becomes a problem when we cannot control the future, and we still try to. Now, so there is something to learn about living in the present, and we'll go back to this when we talk about amnesia. And maybe this meditation and yoga technique could be a good way for also HSC patients who have memory problems to make the most out of their present with some training. And we'll talk a little bit about that. In this case, this is an image. We didn't meet Diane, and we only met her when she had passed away. But Diane, died of Alzheimer when she was 56, and she was diagnosed. So sometimes, it's sometimes the cards that we are dealt in life, and there's not much we can do. Alzheimer and dementia. About half of everybody in the room generally will have had some kind of dementia, by the time they die, including me. There is generally a very high chance. And I started a non-profit foundation last year, really to try to encourage brain wellness and good eating habits and good exercise habits, so that we try to stop this relentless increase in dementia cases, because I think a lot of it is lifestyle and habits. But memory, as I said, it's a central interest of our project, and not only dementia, but of course, encephalitis can affect short-term memory famously. And the story I'm going to tell now is the story of HM, Henry Molaison, who did not have encephalitis, but for some very tragic and fortuitous, depending from which side you see, scientists were very, I wouldn't say elated, but scientists really make the most out of the situation of this young man who lost the ability to make new memories. But Henry Molaison taught us that there are structures in the brain that are essential to consolidate memories, and that's what we learned. And also taught us that you can have a type of memory preserved while you have another kind of memory, so that there are multiple memory systems in the brain. Now, what you see around this brain with an image of this structure called hippocampus, which is central in the consolidation of memory, are the memories of Beth, by the way. And again, if I had the pointer, I would point you to the picture of the monkey, because we found out that Beth was one of the flying monkeys in The Wizard of Oz, which is a nice thing about this project, because we get to know the donors, we get to know our participants really well. So they're not just brains, like anonymous brains, they're really people. So you start learning, we learned gradually to treat brains as people, and vice versa, to treat people as brains, which made us very compassionate and forgiving with people, because sometimes, well, it's not their fault. She said that, he said that, but it's her brain saying it is not her. So it's good. It builds a new kind of empathy and compassion. And the hippocampus. So the hippocampus is central. We talked about, I mentioned dementia and Alzheimer. Now this is a curve, and I apologize for the dryness of this slide, but just look at that line. And remember, before we talked about brain atrophy. Now, this is what happens in general in a normal population to the hippocampus. Again, the hippocampus becomes smaller, and that's why people tend to have memory problems as they age. Again, a normal function of aging. But now let's go back to HM, which stands for Henry Molaison. In scientific publication, to protect the identity and the privacy of the patients, usually it's always the initials that are used. HM stands for Henry Molaison. I'll briefly mention another patient, EP, who we studied. And so this patient was very famous because he was very young when he underwent this operation. He had epilepsy. He started having epileptic seizures when he was very young, around the age of 10. And by the time he was 16, he had the grand mal seizures. So he lived in Hartford, Connecticut. And in the same town, there was a surgeon called William Beecher Scoville who was performing new lobectomies, which were a type of lobotomies. Because the family had become quite desperate for the state of their son, who was 27 at the time when they discussed the surgery, Dr. Scoville suggested that they try this experimental surgery, which was really an ablation of, and this is, sorry, Henry with his parents. He's the little one with the hat. And this is the hospital where Scoville operated in Hartford, Connecticut. And this is the operation that Dr. Scoville was performing at the time, and it was called the middle temporal lobectomy. There were other surgeons, notably McGill in Canada, in Montreal, that had performed this surgery, and it looked like it was beneficial to reduce the seizures. Now, although there was a caveat, because they had performed this operation on psychotic patients, so they really didn't know. The results were that difficult to interpret. It was clear that they didn't have as many seizures, but really they couldn't find out what would really happen if you remove both temporal areas, including the hippocampus, from somebody's brain. And it was a very elegant procedure. I mean, elegant and crude at the same time. Elegant because they were trying to be as selective as possible, but crude because it was really a matter of drilling 2 holes in the frontal bones with a trephine drill, and then from that small openings, lifting there you go. I can recreate it. So let's see. So HM was lying like that. So imagine now that there is a face and a skull, and he made 2 holes in the frontal bones, and he started cutting the tip of the temporal lobes, and then he used some suction tubes to go deeper in the brain and literally suck out tissue, because the brain is not as hard. Otherwise, we wouldn't have concussions in the NFL and all these things. It would be much better, probably. The brain is very delicate, especially when it's fresh inside our brain and working. It's really a matter that can just be broken at your fingertips. So that's why, just a suction tube was enough to remove. And again, because the idea was that it was that tissue that was the origin of the seizures. So you remove that, you stop the seizures. And surgeons still practice this surgery for epileptic patients, but now they know not to do it on both sides. Because when they do it on both sides, something quite dramatic happens, and this is what happened to Henry. Now the speakers don't work, so let's see if you can hear it from my... And this is a researcher interviewing patient HM several years after the surgery. In fact, HM here was already, I think, in his 60s.
When you're not at MIT, what do you do during a typical day?
See, that's what I don't remember things.
Uh-huh. Do you know what you did yesterday?
No, I don't.
How about this morning?
I don't even remember that.
Could you tell me what you had for lunch today?
I don't know, to tell you the truth. I'm not...
What do you think you'll do tomorrow?
Whatever's beneficial.
Good answer.
Well, this last bit is very important. Okay, there you go. Because, you see, there was this very severe memory impairment. But when he was asked, we're doing tomorrow, he's like, whatever is beneficial. I mean, it shows that his intellect was still there. In fact, his sense of humor was still there. And so what was special about Henry is that after the surgery, everything else was intact in his way of relating to people, but he had this deficit. At the moment they started probing his memory, he showed a very dramatic failure. And so that's why after him, they never performed that type of surgery anymore. Because that's always the question. I should just say that before. No, good question. It did to a certain extent, but seizures, he continued to take medications for the seizures all his life. Dilantin being one of the major prescribed medication at the time. But another interesting fact is that when this is a star that's used in neuropsychology experiments. It's like learning a maze, but it's sort of the same type of task learning. And at the time, HM had this very dramatic memory impairment. But then he was asked to trace, between the contours of this star, only using a reflection of his hand. So we have this little gadget in our lab, and it's very difficult because it's like when you're trying to write on a window for somebody who's on the other side. You need to kind of train, and you make mistakes at the beginning. Then you're actually brain very quickly, if you're intact, then very quickly learn how to do it. And so they thought HM would fail. He would not be able because it's a type of learning. But instead, he was very good. He was very good at this. So that was extraordinary. And that's how they started thinking, okay, wait a minute, memory is not just one process, but there is this kind of memory that doesn't rely on those structures that were taken out, obviously. And it's procedural memory, which is really the kind of memory that you engage when you learn the guitar or the violin, what they call muscle memory, and so on. So it's very interesting that HM also showed this dissociation between memory functions, which we see in also a patient with encephalitis who have a memory impairment, but they're able to learn new tasks. And these are the lesions, remarkably, again, similar to some patients with encephalitis that we've seen. And it shows, again, this is an MRI of the brain. And in this case, the ones that I showed you before, they were coronal images. So it was like a plane that was cutting the brain in this direction. So this would be the plane of cut. In this case, now we're looking from above the head. And in fact, you can see the eyes from the top and the tip of the nose as well. So it's a different view, but it shows really well the temporal lobes. It's a good view to see that. And when you see this space here should actually be filled with brain. But that's the tissue that the surgeon took out back in 1953. And this is an extremely recent scan. Bless you. And this is Henry, a little later. So you can see also, his attitude was, he was a very placid person, a very good character, very good demeanor. Also because another structure that had been taken out was the amygdala, which tends to be the structure also involved with fear and, the sort of more emotional reactions that we have, including anger. So he seemed to have been very placid all along. This is him when I met him in Hartford. Oh, it got cut off, I apologize. And so he died when he was 82, and he did something also very generous. I mean, after having participated in hundreds of experiments for about 50 years, he was also generous enough to leave his brain to science. And in fact, this is a cast of his brain. And so this is the brain that changed everything, because this is, when HM died, his identity became known. The conservator decided that it was okay to now disclose his personal identity. And so, in fact, we have the author of this article right here in the room, and he's the guy now who's a little embarrassed. So, spot the embarrassed one. And I encourage you to read it because it's a beautiful narrative. And in fact, Luke is also the grandson of Dr. Scoville. So he has a very personal view. And he's writing a book now on memory, the brain, and the lesions that cause memory impairment. Now, they changed everything because, again, this was a really important brain for neuroscience. It taught so much in the science of memory that we were asked, we got a grant from the National Science Foundation to examine this very famous brain to find out, is it me? Yes? Maybe it's the Lavalier with this mic? No. Okay, hope you don't mind the little crackling noise. We had to, MRI, I will show some slides later. It's a beautiful tool because you can look at somebody's brain without having to take it out, because we cannot put it back yet. That's the problem. But, it's a very low resolution. So we were asked to really find out what had happened in 1953 during the surgery. And this is the picture of the real brain from the ventral side. So we're looking from the brain upside down. And it shows again here the temporal lobe. The eyes would be that way. And so this is the temporal lobe. And here you can see the lesion that the surgeon made. But we went beyond that, of course, and then we processed the brain. And it was a big ordeal. We had to slice the brain to create this glass slice to study under the microscope to really find out what was the basis of this amnesia. in the real brain. And so this is me in the lab when in 2009 we sliced the brain with this very elaborate apparatus. It was quite an adventure. But the result is it was very wonderful. So this is how, I don't know if you want to know, but this is how we slice brains, the real ones. You know, we freeze them inside a gelatin cast. And you can see there's actually a blade on the left, and the microtome, this instrument, runs the block under this blade, and we slither off these very, very thin layers, about this, they're as thin as a hair, as a human hair. And this brain was sliced into 2,401 slices. And this is how this is the real speed, by the way. So it's a very long process, but it's the only way to really find out what is happening in a brain from a pathological standpoint. So MRI gives you a global view of the brain, of a pathology or some disease, but to really find out those features that underlie this disease, you need to do this. At least until they'll build some MRIs or some new instruments where you can do it non-invasively. And this was the result of that. We were also taking some photographs from the top. And so now we're kind of doing a movie through this brain, going, you know, we're still in the frontal lobes now, and imagine it's like pretty much navigating through the brain. And then we were very excited when, at this point, when the temporal lobes started to come out here. We were very excited because we were the first people to see actually the brain after Dr. Scoville, so after more than 50 years. We were not the only one, because I was broadcasting this on the web. So actually we were not just in the lab doing that, so everybody could see it. Now, this whole movie is actually made of these 2,400 images, 2,401, and then we reconstructed the data using these big workstations. And so we were able to really find out what happened. And we found out that some of the hippocampus, in fact, half of it had been left behind. So now this paper has just been published, so it's going to be very interesting to see how memory science is going to kind of be looking at these results and say, okay, well, HM wasn't completely pure hippocampal lesion patient, so maybe memory doesn't rely on that bit of it. So it's going to be very interesting. This is how science progresses. But I'm talking about this even if it's a little pedantic, because it is really the only way you can then with certainty understand what was happening in the brain, at least in the human brain. Animal studies utilize experimental animals that, whether you agree with this fact or not, ethically, you know, we can be invasive and we can get some answers with the live animal that we cannot for the human being. And very interesting enough, our project is always in the boundary of art and science. So this experiment inspired a theatrical play that was run in the UK called 2,401 Objects, and it's based on the story of HM and the story of his brain, the way that we processed it in our lab. Because these producers were looking at us cutting the brain and they got inspired. So that's the man behind the brain. There is always a man or a woman behind the brain. Remember that. There's always a good woman behind the good brain and a good man. All right, I won't get into that. Now, and this is EP. So now here we're getting a little closer to what, you know, closer to our concerns. And EP had contracted HSC, but when he was quite old already, I think in his 70s. And this is an issue of National Geographic about memory, because EP had pretty much, in fact, a much purer lesion. So imagine that HSC is like a surgeon that does what Dr. Scoville did to Henry Mollason back in 1953. HSC doesn't really pay attention to medical literature. So it doesn't know that if it affects both hemispheres, it will create a memory impairment. And so unfortunately, it spreads primarily in the medial temporal lobes. And EP had suffered a profound amnesia as well due to HSC, remarkably similar to HM. So HM and EP are two models, two different situations, but the two models for amnesia that are very, very important for neuroscience. They've been studied. And in fact, here is an MRI, again from the top, showing, and here what you see bright is actually the lesion, because it's a different type of sequence. But they're remarkably similar, and their impairment was remarkably similar. Now, I'll spare you the nuances, because, you know, it depends if the lesion is more lateral. There's a difference in the retrieval autobiographical memory. So when we study brains or MRIs from these patients, it's really putting together all this little information, and we run a long battery of neuropsychologic tests to try to tease out, what they can do and what they cannot. And also these patients are very good at finding cues, even if they don't have memory, even if they're unable to make memories to remember you, they find cues, very clever to find cues to then pretend, so to speak, to have the memory. And that shows also that the level of intelligence, remains unchanged. And I don't believe that the brain is made of different parts that do different things necessarily. I think it's a network that involves multiple structures. But it's very fascinating to just see that when there is a localized lesion, it affects only, parts of the way that we are, of our behavior, and doesn't just decrease all of the behavior by a bit. So we don't become a little more forgetful, a little less clever, a little less reactive, or a little less strong. Things are taken very selectively. And this is the brain of EP. And here you can see the lesion as well. In this case, the encephalitis, I'll show you in the next slide, of course, is not a lesion that it's like a surgical cut. It's more likely the brain that what we see in the brain is I think it is. That wasn't me. It was, see, it is more a destruction of the tissue, of the brain tissue. So the cells and the fibers deteriorate in this area because of the viral infection. And depending how extensive it is, it affects more of the temporal lobe or not. That's why, again, treatment is very important. And another thing is that, the cases like PP are extremely rare now, fortunately, because generally, the encephalitis is treated. Now, this is an exceptional group. I think it's an amazing opportunity also to find out a little more about using these methodologies, and especially imaging, that we now have some very sophisticated imaging and also sophisticated batteries of cognitive tests. But a group like this, you're very, I think this is extraordinary that you guys decided to create this group, because otherwise, scientists like me have a very hard time finding this type of patients. It's very difficult when instead they could shed so much light into the way that the brain works. In return, I think that research in return can do something for you, which is to really help to change policies. Because once the papers, like the paper on HM and the paper of EP, they've been published on very high-level journals, and it's evidence that you put out there for policymakers to see, to use, and because these events are tragic. So one thing that we do in our program is to make this research very visible, maintaining, of course, confidentiality and privacy, because that's very important. Now, this is a Victor Hugo. I mean, I love this cover because it's the postscript of my life. And so in our program, there is about 350 maybe. I think Ruth, who is also sitting at the back of the room, she will tell you, and she's our program coordinator. But there's about 300 and 350 people that are working around San Diego with a card that they belong to our brain club, and eventually we'll print their brains and give them as a present. So when we get there, well, because we want to maintain this relationship with these donors, and they're alive. I mean, we image them longitudinally, but they also all have one thing in common, that they donate the brain. And this is, as I said, very important, because it's only with the real brain that we can find out what really had happened to this person. Sometimes a person may have dementia in the family, and the doctor will tell the family that it's Alzheimer, but the spouse will tell us, no, this is not Alzheimer. I know when I talk to him, it's not that. And guess what? Then usually the families are more correct than the doctors when we look at the actual brain. And this, again, shows the importance of very, very careful and caretaking, because it's not just the patient or the doctor who gives information. I mean, we collect so much incredible anecdotal information from the caretakers, because those are the ones who really spend time with these patients, and it's very important to hear what their experience is of the disease. But this is what I was saying before. I hope there is enough light to see. When you zoom in an MRI image, soon enough you don't see anything. It's really the crappiest digital camera you could buy. I don't think you could buy such a bad digital camera these days, not even for a dime. Certainly not kids wouldn't buy it. now they use the HD. But obviously it's a non-invasive diagnostic tool. It's exceptional. But so we are interested in knowing why one of these pixels is bright and the other one is dark. And the bright pixel is a lesion, and the dark is normal tissue. So, and we need to go underneath. And this is a slide. The brain is like an impressionistic painting. If you look at the structure under the microscope. So just like pointillism, in this case, this painting by Seurat, it's the same idea. You see a texture, and what MRI sees is the painting, but it doesn't see the way it was done. So here, when you look at this type of paintings from Surrealism and Pointillism, you see that it's very similar. And in fact, this is the hippocampus below. And when you zoom in the hippocampus, you see really the cellular structure. And that you cannot see with MRI. And when there is a brain disease, it's the cellular structure that becomes damaged. And that will give you information to treat it. So if you want to learn how to treat a disease, you need to do this. And the way we do it, you've seen the cutting. And then this should start. Then these slices that you saw, we mount them on glass. So it's a very careful and admittedly tedious process. And I always make the analogy of the brain as a book. And when we take these slices, it's really kind of like leafing through a book. And every page, though, doesn't really have ink. It's like magic ink. You have to treat these pages. It's fortunate and unfortunate. But you treat these pages with different types of dyes and molecules or antibodies, and you see these features that you want to see. And by now, after 200 years, we know what to use to highlight Alzheimer's pathology, to highlight neuronal degeneration, or to highlight, for example, fibers that have been then pretty much damaged also by the encephalitis, which is a technique that we use in our lab. And then we digitize. Now, the exceptional thing, as I said initially about our project, is that we want this information to be available to as many researchers, doctors as possible. So we digitize all this information, and the brain becomes, as I said, this kind of series of pages, which are actually glass slides. But then we use Google. So now our programmer created Google Maps of the brain, just using, because Google they put their software for free. They're called APIs, this programming language. And so our programmer took this language and they adapted it for the brain. So if you go on our website, you can actually zoom in. And we're zooming in now the temporal lobe of a healthy individual. Because what we found out from HM analyzing his brain is that there is this area in the brain called the entorhinal cortex, which is close to the hippocampus. Now we're looking at a cross-section also running perpendicular to my gaze. Okay? And this is, I think as a scale, we're talking about maybe 3-4 millimeters here. But you see, this is the entorhinal cortex. We recognize it because there are these little blobs. And that's the gateway of all the information that we gather from the environment into our memories. And both EP, HM, and other patients with amnesia, that structure is destroyed. So HM had some hippocampus left, but still could not make memories. But this area called entorhinal cortex was damaged. So now we're narrowing, our target closer and closer to what really enables us to make memory, not just the medial temporal lobe or the long hippocampus. Now, thanks to the studies, we're narrowing it down to the entorhinal cortex. And now this is a normal individual with a nice, beautiful entorhinal cortex, so we can zoom in, and you're able to do this on the web. And we're going to zoom in on layer 4 of the entorhinal cortex. And this is sort of the resolution that we get out of these images. They're enormous images. We use these very large scanners, and they're actually made of 60,000 little tiles that we stitch together. So it'll be like one brain digitized like that is like 1 billion ebooks on the Kindle. Or if you stream 3,000 years of MP3 music. This is the information that we gather from one brain by doing all this process, which is then available on the web. So let's say streaming the brain and listening to it. So we're getting some answers now with this process. And these are the answers that are crucial also to study encephalitis, because again, every individual has a different pattern of damage, which is reflected, if you look carefully, and if you test these patients carefully, it is reflected in their behavior. And you have to be very, almost crafty to really understand what is happening in the mind of an encephalitic patient, or just like it was HM, even though that was an actual surgery or EP. Crafty in the sense that you have to be very careful not to give cues and very careful to tease out this process and there are hundreds of tests. So patients, I don't mean to discourage you because I hope that you'll be willing to participate. But really the tests are long, an hour, 2 hours, and we combine it with neuroimaging. Now, but the information that we gather now on the patients who donated their brains, who passed away, we use that to interpret the results that we have on patients who are alive and we want to help while they're alive. So in a sense, the people who donate their brain when they pass away, they're really doing it altruistically to help other patients like them, even if it's not a direct benefit to them. And this was really HM's motivation. And so HM's brain is still a model, is still like the yardstick in which we measure amnesia for other HSC patients too. Now we know what's underneath this gray pixel, and this is really what the brain looks like inside. It's a big mess. It is a big mess. It's just all this. So we saw the cells, but these cells communicate with each other, and they do it with wires. There is some wireless connectivity in the brain, because of course there is electromagnetic activity, but there's still a lot of wires. I mean, it's like if you go to the back of a computer, you're already at home. How many wires? Isn't it annoying how many wires we have out of a silly one little computer, and it's always garbled. Well, the brain is a mess. And so these fibers are about 1 micron thin. I mean, they're very, very thin, like a thousandth of a millimeter, if you can imagine that. 3 or 4 thousandths of a millimeter each of these fibers. And they all connect different areas of the brain. So we're trying to make sense out of this mess, this organic mess. That's why, again, don't be fooled. The brain, when they show you pictures of the activity in the brain and it looks great, colors flashing or freeways, it's not like that. It's actually a very complicated mass. The brain is an organ, just like our kidney or our liver. It's just complicated. It's not perfect. It's susceptible to disease. We got to feed it well. We got to treat it well. So, but we rewrite algorithms to try to detect the orientation of this fiber and gradually build a map at this level of resolution. Because, for example, a lesion that's caused by an encephalitis, will have an effect on other areas of the brain because that region of the medial temporal lobe is connected to everywhere else. So we need to learn, and we learn also from the patients, what is connected with what. And now in neuroscience it's called the connectome, a very, very intimidating name, which makes it even more difficult to study. They should have called it something more friendly. And I'm sorry. And so again, and it's not just a mechanistic approach. Like, okay, you got a car, you have the radiator that fails, and you have a problem with your car. This used to be the old way of looking at the brain, because there was this idea that it was a perfect machine, designed perfectly, and that if something broke, you could define exactly what went wrong and find out what happened. Now, there's a little more than that. Even a lesion, I think that what we've seen in other patients with these medial temporal lobe lesions that were caused by encephalitis is that doesn't affect their creativity or their wits. But I'm very interested in how somebody can be creative in anything that they do, cooking or painting or even attending to their children. I mean, there's creativity everywhere in our behavior. And in fact, it's really, there are many unsung geniuses and heroes who are not celebrated painters, but that they use their creativity and genius in many little things, including sense of humor. A good sense of humor, a witty sense of humor is a sign of genius. And patients with lesions in the medial temporal lobe, because they have these features preserved, they're also a window into understanding what is creativity in the human brain. Because they have a very, very dramatic impairment, but it doesn't affect that. In fact, sometimes it unleashes creativity. We've seen a patient with an incredible sense of humor that nobody could have. It's just like a machine of jokes. So it makes you think, okay, so Jay Leno, maybe his medial temporal lobe, or other comedians, their medial temporal lobe is maybe a little deteriorated. So we should enroll these celebrities, comedians, but we understand that from patients, and it's not straightforward as a concept. And this just to stay in the color theme. These are all the tests. If you're asked, this is called the Stroop test. This is something that Ruth administers. If you're asked to read this very quickly, you will tend to sort of prioritize the language component rather than the color component. And so it is a measure of executive function because you got to check that. It's similar to the STAR in a sense because you got to always correct your errors as you make them. And so, but this involves the frontal lobe. So this is a personality test. All this to correct, like I said, we're kind of Renaissance painters of patients and trying to make a beautiful portrait, and then people will be able to look at, and with modern technologies through the web. And the project is called Digital Brain Library. Yes?
I'm Morris. I hear you about all the tests and whatever, but what my biggest worry is about the test, I had a lot of tests in, and the end result was that I could not work, and I mean the test results are in the cupboard, and the cupboard is digitalized, and wherever my name comes up, whether it's municipality, whether it's government, whether it's my driver's license, whether it's my passport, bloop, there comes the file.
What do you mean there comes a file?
There comes my file of testing, that I have, an IQ of left of 152.
So it was in the public domain?
It's in the public domain, yes.
Because maybe those testings were done not in a research setting, but they were done in a clinical testing.
Yes.
Yeah, and that's the difference. If those testings were made, if those tests were made to the effect of checking whether you could drive or not drive, that would be in the public domain. I don't know, because in the research setting there are very strict regulations and HIPAA concern for private. In our case, some of our participants they don't want to be anonymous, so they want to, because they have that idea of, because we like to associate the person with the brain. When some kid is going to visit our lab or our brain museum and is going to play with their brain, they want their portrait there, so they know, the kid knows that, or the doctor will know that this is a man. We think it's important because also you could anonymize a lot of things, but the more detailed biography you leave together with this enormous amount of data, why do all this work if these then are going to be just anonymous brains? But there are some legal implications and ethical implications too. In the research setting, there is a safe assumption that the data is completely private. However, we have been sharing data with the patients so that they can then use this information to request services. Yeah, but it should always go. I believe that what we gather is owned by the patient. They contribute to our project in return. We give them information and they can use. Our participants regularly ask for a copy of the MRI. It is a little risky because there is liabilities involved with that. If I'm not a radiologist, a trained radiologist, so if I examine somebody's MRI and I don't notice that there is maybe an aneurysm because I don't really read scans for a living, this person could then one day sue me because, you had this scan all along and you never told me I had an aneurysm. So there are some issues, but it's a bit of a risk. But still, they are very grateful of the data because then they can use that when they need it. It's really your brain, it's not ours. It's your life, it's your brain.
I mean, all the tests that were done, were used for, have a tailor-made program and I trained for 2 years in an institution and whatever, and I came back, speaking English again, walking again, not being able to count, but I mean, I could still calculate, so I mean, that's fine. But what I find out now in the Netherlands especially is that they start using your file, it starts following you. Now, I don't mind because, I'm on a disability patient, but suppose you're 18.
No, of course.
And that's why I'm very worried about what
well, so there are many databases of thousands of patients now in the public domain. Public, there is a data usage consent, of course, and they're anonymized. We have so if you're not if one of our participants is not comfortable with any aspect of our research, they don't consent to it. So our consent is not like, would you like to join us? Yeah, great, thanks, sign here. No, it's a long list of things, of tests. And you can say, I'm comfortable with this, but I don't want you to test my IQ. Fine. Obviously, we like to have all the information, because there is so much work involved in following this person through their lives and then do this project with the brain, that the more information we have, the better it is. But you cannot force an individual. So, and this is also revocable. You know, if somebody becomes, for any personal reason, uncomfortable with the idea of having this information, the information can be destroyed. It's a conversation. That's the difference. It's not like it's citizen science. These days, and Google Health, and there are many providers, in fact, you are the keeper of your files, not the doctor, and you decide then how to use them to your advantage.
It's funny that you mention it, because it was on my IQ gap that was, about 40. But my employer said, I mean, sorry, I mean, you can't count anymore. You're a financial director, sorry. I mean,
and this.
40. And I said, I mean, IQ gap is just now. I mean, who knows? Because I'm a strong believer of training and training and training it. But if you're HIV, it's fine. But I mean,
I don't know if you know about eugenics. I mean, there have been many abuse of personal information, and one of the ethical worries about genotyping, having your DNA mapped, is that some people are concerned that information will be one day used to block your, if your kid, we know the gene that associated with mathematics, they'll say, oh, no, we're not going to waste time with this kid to go through math, because his genes, he's not able to do it anyway. You know what I mean? But these are ethical concerns. And it's an open, this is like almost like, what do they call it when politicians go out and have the town hall meetings? Yeah, I mean, that's why you're here. I mean, this is also to discuss these issues. It's up to you to come up with some rules for us. This idea that the scientists know better and it's BS. Excuse me. This doesn't go in YouTube. Meaning you decide the policies and we follow these policies. And individual wishes or level of comfort can be different, but I think you have the opportunity, especially these days where you're all here, to kind of talk about these things. And then there can be a dialogue between you and the researchers, and to say what would be the most mutually beneficial approach. I think that the research that we do can help you get more out of the system. And there's no stigma associated. And especially now, we're in luck, because there is a lot about neurotraining. It's common knowledge now that the brain is not something that cannot rebuild itself or rewire itself to work. So I think that's information that it's on your side too. Just like stroke. Stroke, there is an incredible recovery. And this, although there is permanent damage, but there are ways in which you can compensate for it. And there are areas that are less damaged. That's why we study it, because we want to know what remote damage is done. When we see a lesion that is so apparent in MRI, now there are other lesions in different parts that can be more subtle in different parts of the brain. So we want to account for those, because it may explain the IQ. The 40 points in IQ may be explainable, and maybe we can get a hint whether that's reversible or not. But I think the information is yours, you see.
And the judgment is theirs.
But, well, unfortunately, I hope I don't sound disrespectful, but unfortunately, it is a bad thing. I mean, it's not. It is. The encephalitis. I mean, I've seen patients with terminal illness like ALS that died. After a few months, they wanted to donate their brain. I mean, it sucks. It's not a happy event in somebody's life to develop. And I've just spoken yesterday very briefly with some of you, and obviously I cannot even imagine what it's like. And the first question is, why me? Why the hell is this happening to me? But I've seen patients who were diagnosed with Lou Gehrig disease and die in the arc of a few months, and why them? I mean, it's really the situation and how to make the best. If this research can help you also being engaged and be more aware of your brain, it will help you, because then it's not like a black box. It's not like
to make the best out of it.
To make the best out of it. I think information. I think if you know that your brain looks like this, these lesions, you know yourself better, and then you live your life I think, a little better because you're always aware of what's going on. If you just don't even imagine your brain and you let the doctors tell you in very complicated terms and you don't even look at your own scan, we scan individuals in our program and they become more aware. And frankly, they become proud of their brains too. They say, because they know we care so much about the brain. And then they say, oh, how did I do in this test? So now we're designing nutritional programs for them, to see whether it can. But it's really a self-awareness. And if you have, forgive the term, a handicap, but let's look at like a handicap in golf. I mean, like a sporting, you start with a disadvantage, you have a disadvantage, you make the best out of that. It's the only thing we can do. Yeah, it's like if I were a basketball player in the league, I'd be very short and it'd be a disadvantage. But if I really wanted it, I want to play. Nobody's going to tell me I don't play. And I just have to work extra hard. So, but I'm almost done. And I'm glad, that this is really because I wanted to tell you today a little bit about our program and about the brain, showing you really, real brains without bringing a real one. But, I'm also would like to be educated in what is the context of encephalitis so that I can also fine-tune the way that we operate, because this is fairly new to us to work with patients like that.
May I ask a quick question?
Mm-hmm.
So in the case of persons like myself with autoimmune forms of encephalitis, do you think this slice technology will be able to, or has it been able to learn what the changes are?
What the mechanisms are.
Because I think so it is, as I understand it, not well understood why there is such impairment sometimes without lesions being apparent in any extent on MRI.
On MRI. Well, but you see, so if we go back to this.
That's why I wanted.
Right, exactly. So this is the multiple sclerosis, another autoimmune disease, and HIV. We're mentioning HIV, in AIDS. This is in fact, this brightness, radiologist would identify it as a lesion. In this particular scan, it's a hyperintensity. Again, another not unnecessary complicated terms for like brightness, but it's hyper intense. I mean, this pixel is hyper intense, but they don't know what is happening there. So these fibers here, there are two things that happen in multiple sclerosis. The myelin sheath is the insulation on the fibers, which is also now we know a very dynamic process. It's beautiful, actually. The cells that build the myelin, the insulation, they don't just build it and go away, and then, if it breaks, it breaks. It's a constant change. And in fact, it determines also which neurons talk to each other, because once you put this insulation, you cannot make a contact with it. And once you remove it, you can make a contact. So you can imagine even a disease that causes demyelination may open the door to new connections. I mean, there's so much we don't know. But the thing is that by doing this histological work, we're beginning to show what is behind these hyperintensities and what is really the process. In this case, for example, this is a healthy bit of white matter. I apologize, I didn't talk about white matter and gray matter, but essentially these fibers that we see is the main mass of the brain. The gray matter is the cellular nuclei or the cerebral cortex. Now we're talking about white matter. And the white matter, this either damage because myelin is degraded in these autoimmune diseases, or it could be a destruction of the actual fibers, which we've seen in viral encephalitis, which of course we see when there is a lesion in the brain, and there is what's called Wallerian degeneration, and the degeneration travels along these fibers, and gradually it reaches the neuron from which they originated, and the neuron dies. So that's why we have all these remote effects. But the process, however tedious and quite expensive too, it's really important to find out, what is really happening, as I said before, because otherwise you only get an indirect image of what's going on, a very global effect. Very important, though, because if you do it regularly, you can see how this disease evolves. And these lesions come and go sometimes. It's not a pattern they fix. And this lesion also happen with age. Now, we can have, if you like, we can have, I'm reaching the end of my hour, so I'll finish and then we'll do questions. Okay, because I only have a couple more slides. So I know I finished in time. But this is sort of a data portal. So this is what researchers can see from our portal of the project. These are dots. But as I said, some people like not to be anonymous, at least in the context of our project. And so what I like about this is that we actually put a face to the brain. And so this is a way in which you can learn a little bit about the donor, about their own personal, In this case, this gentleman, he's healthy. He's healthy in very many respects. As you'll see, he has a healthy love life as well. He's 97. And so the experience I like to leave, I'd like to leave posterity, so to speak, is really the connection between the human being and the neurological data, so that also doctors or students start training into looking at disease and to looking at patients not as just cases, but as people. And I think the way to do it is by showing, it's interesting that this symposium is called Faces, because, we always put a face to the brain, actually, and it's very serendipitous. And, so together with the strict neurological or medical data, we also have, biographical information, and Charles gave us the pictures when he was a kid, and so we kind of have a little short documentary about his life, which will hold clues maybe in the future when they will know a little more about how our experiences influence our behavior or our disease. And so this is him. I like to take photos. I'm very intrusive. I always get into these people's lives. I go to their homes. Yeah, and this is Charles. So again, I think the volume, and we do interviews with our patients, so this is Charles.
So love is a wonderful word. L-O-V-E has 13 different definitions that I know of. And I think I've experienced them all at some various times in my life. In late life, I've been afflicted with a need for love. One of my friends says, "You're in love with love." And I try to argue with him, but it doesn't make much sense. He doesn't know what love is, but I do. And I enjoy it very much. I've had I don't need to go into varieties of love. Everyone else knows their own thoughts. And I agree with you. Whatever you think is true. Love in old age is the interesting part. At the present time, at 97 years old, I live with 130 other people. 100 of them are females. And of the females, I have a groupie, probably 6 or 8. We have affection for each other. Some of them call it love. It's amazing how any attractive younger woman of, say, 80 can think of me, an old man who is beyond hope for any activities. They still say, "I love you, Charles." It's wonderful. Thank you very much.
So this is the brain library. And then just to conclude, so again, the vision is to have a repository of data that is rigorous scientifically and follows guidelines in terms of privacy, unless there is an explicit wish from our donors to be our poster child. So there are some of our donors, like Beth and Charles, who are our poster children. They help us also. He's very kind in lending this video, because then it helps me talk about, really explain what I'm trying to do. And we also are very involved in community outreach. We work with other non-profits. In this case, we were taking these videos and pictures of the brain for a non-profit in the UK who is trying to, in fact, advocate for removing stigma from, from mental illness and looking at mental illness as any other organic disease, so that somebody with a mental illness is not discriminated. So, we welcome them in the lab, of course, because they know we have many brains and they wanted to take these images. And we work with museums. In fact, I'm working to put together a brain exhibition here in San Diego, but we've given material to museums, again, to show, these are the glass slides that we digitized. We're talking about putting this on the glass slides. And this is an exhibit in London at the Science Museum, and there was a memory exhibit, so we gave them some material from Henry's brain. And then we have tours and kids, and we go to the schools, and this is that's not a real brain, by the way. That's why the 3D printer comes handy, because that guy, that's the next generation neurosurgeon right there. He's already taking it apart. But it's important because again, I think that in terms of dementia, nutrition is going to be very important. So we want these kids to become aware of their brain as soon as possible, and not only the idea don't do drugs and drugs are bad, but really just let them figure out eventually, once they know that their brain is very important for them and that's their opportunity right there, then they'll make the better choices. And that's what we try to do. So this is my phone number, the email. There's also Ruth. Ruth, can you raise your hand, please? So Ruth, if you have questions about the project and how to enroll, naturally we tend to work locally, although we have flown in some patients in certain exceptional circumstances, if the patients are VIP. Can you make the VIP list? Let's say. So VIP meaning that it's a case that we see from the imaging is usually the first step, and if you most likely have an MRI, it would be very interesting to look at the MRI, and we have a consent form that allows us to access medical records, again, following HIPAA and privacy regulations. And that's usually the first step to assess the topography of the lesion. After that, the tests need to be done here, although, we could fly to you. Generally, being local is, and regarding the brain donation, that's something kind of, I have my brain donation card, just keep it, put it on the shelf and keep it there. Because again, it's very important to be able to eventually really understand what's going on, because MRI is not there yet, and there are physical limitations in the MRI technique that I don't think any physicist can resolve. So unless they come up with a complete radical new imaging device, I think for now we're stuck with real brains. Yes. Thank you.